I'd like to introduce Brian Davis, who is going to be our seminar speaker today. He's a research fellow in the Intelligent Vehicles Laboratory in the Mechanical Engineering Department at the University of Minnesota. He started at the university as an undergrad in 2005 and subsequently completed his thesis-based master's degree in 2012 on new technologies for mileage-based users fees, which back then was very controversial and is even controversial today. It's become a fairly hot topic. His research has spanned a diverse range of topics within what is called intelligent transportation systems, including sensing technologies such as computer vision, centimeter-level GNSS and LiDAR, and innovative programming solutions using embedded computers, cellular communications, and database servers. He's worked on projects dealing with high-accuracy digital mapping, driver assist systems, and lane departure warning systems. And besides all that, he plays the trombone and the bass guitar when he has time. Anyway, without further ado, Brian.
Thanks. Right, so, like Professor Donat said, my name is Brian Davis. I'm from the Intelligent Vehicles Lab here in the ME department. Today I'm going to talk to you about a project I worked on called In-Vehicle Dynamic Curve Speed Warnings at High-Risk Rural Curves. So I'm going to start with the motivation for this project. So I know a lot of seminar speakers have showed you these statistics, but fatal motor crashes are a big problem in the United States and in the world also. But 37,000 people passed away due to traffic accidents in 2016, according to NHTSA. And in Minnesota, 375 traffic deaths in 2015. That's the most current data available from the state. Even if you look at Minnesota against other states, the number of deaths we have per vehicle miles traveled is up there in terms of, or up there in a good way. It's among the lowest, but it's still an issue for Minnesota Department of Public Safety and Minnesota Department of Transportation, who are very interested in looking at different ways for addressing this issue. So looking at motor vehicle crashes in Minnesota, looking at system-wide fatal crashes, so crashes with at least one death anywhere on any road, over half of them are due to lane departure, and 70% of them are on rural roads. So digging a little bit into rural roads, so for severe crashes on county roads, 65% of runoff road or lane departure crashes are on roads with relatively low average daily traffic, so less than 1,000 ADT. 46% of lane departure crashes occur at curves, as opposed to all other locations. And then 63% of curve-related crashes are on these low ADT roads. So this motivates a solution. One possible way to do this, and to some extent it's being implemented throughout the state, is static signage. So normal curve speed warning signs that say curve ahead or have chevrons, things like that. The manual uniform, the MUTCD, Manual on Uniform Traffic Control Devices, only requires the signage on roads with over 1,000 ADT. But like I showed in the last slide, roads with very low ADT are particularly at risk. Other solutions include dynamic curve speed warning signs, so signs that change their message based on either the vehicle's position or speed relative to the curve. Studies have shown that these techniques are effective, but they're also very expensive. So it's costly to maintain, it's costly to install into curves. And again, because roads are the high-risk roads are so low ADT, it's hard to justify putting these signs up because there are so many of these low ADT curves, and with so few people driving through them, it's not always a major priority for counties and state engineers. So that motivates the solution that we looked at, in-vehicle warnings, specifically for curve speed. So we proposed a system to deliver in-vehicle warnings to drivers So visual and auditory warnings based on their position and speed relative to the curve. The advantage of this technique is that instead of having to put infrastructure at every curve, you can maintain digital infrastructure or maps of these curves and then use a phone or a car's GPS sensors to determine when and where to display these warnings. So when thinking about a system like this, system requirements include that it's not distracting. It has to be safe. It obviously has to be safer than navigating the curve without the system, but also we don't want to add any mental workload to the driver's task. It needs to be effective and also needs to be usable. So that means that the system's easy to use, easy to understand so that drivers aren't going to disable it, or if they think it's annoying, they might turn it off or turn it down. So it needs to be useful for them enough that they want to use it so that they get the benefits from using the system. So we chose to implement this system on a smartphone. We used a smartphone just because it integrates GPS, it has a screen, it has speakers. Smartphones are ubiquitous among almost all drivers, so it was a good platform to test out the warnings. So on the phone, it stored a map of the curves that we were testing. It had information such as its position and the advisory curve speed. And then using the phone sensors, its GPS, for vehicle position and speed, the software could determine when to show a warning to the driver so that it's close enough to the curve that it's useful, but not so far away that they forget about it. So in designing this system, we also looked at the warning criteria, so when and where to warn the drivers. So that means as a driver is approaching a curve, where exactly do they see the warning? And under what circumstances do they see it? If they're going the speed limit, do they need to see the warning? If they're exceeding the speed limit by a lot, should they see a more severe warning? Questions like that. Also, what warnings do they actually see and hear? So the visual and the audio warning messages, that's a very important component. So we came up with some candidate designs, and then we used user testing to hone in on the designs that we implemented on the smartphone. So this collection of warnings is what we considered for the different visual messages. So our basis for designing these warnings was to build off of existing driver knowledge of curve speed warning signs and existing speed limit signs. And then in order to differentiate different severities, we used color, so white, yellow, and red. So based on the usability testing, we found that the top left set of warnings was the most preferred. And I'll note that what the red and white alternating signs represents is that on the phone that would be flashing. So again, this is the visual warning that we selected. And then this component would flash when they receive a red warning. So the auditory message selection was another thing that we looked at both in the literature, and we used user testing to help figure out exactly what we want to say. So the question here is how best to order the information. So we split the possible information the driver might receive into three main groups. So context about the warning, so that would be why they're receiving the warning, curve ahead or some obstacle ahead. The command that we want them to do, so reduce speed, and then the distance to the event, so that gives them additional context about how much time they have to act on the warning. So based on testing and then also looking at considerations about message length, we wanted to make sure that the message was not so long that the driver would have to spend a long time listening to it to understand what the important information was. So we selected this order, context and then command. So for our case, that would be curve ahead, reduce speed. And then in addition to this, we had an even shorter version that was just reduce speed that the driver would hear if they were so close to the curve that we didn't want to spend the time playing the entire message. So going back to the warning criteria, where and when to warn the drivers. So the considerations for this, and I touched on this a little bit already, but the warnings need to be timely. So they need to be close enough to the curve that the curve is upcoming and they can see it and they understand that they need to take some action due to it. It can't be so far away from the curve that once they hear the warning, they have time to forget about it before they need to act. Additionally, it needs to be non-distracting. So when the driver is actually navigating the curve, we don't want them to be interacting with the system. We want the system to be as undistracting or non-distracting as possible so that while they're doing the difficult task of navigating this potentially hazardous curve, they don't need to hear or see any information about the curve. And the warnings need to be applicable. So if someone's driving safely, the system shouldn't annoy them. It could give them additional information, just as a reminder, but someone who's driving safe probably doesn't want to hear warnings over and over and over again if they don't need to. So this is the warning criteria that we selected. And I'm going to talk through this image. So we split the approach to a curve up into 3 checkpoints. And these are virtual checkpoints based on distance to the curve. So at the first checkpoint, the system simply just shows a yellow curve ahead warning. And then it shows the sign with an appropriate right or left curve. And then it shows an appropriate advisory curve speed. And at this stage, it does not play any audio, regardless of their speed. So then at checkpoint 2, they continue to see the yellow warning, or they'll see the red flashing warning based on their speed. So if they're exceeding the curve speed, or if they're under the curve speed, the approach speed. So the signed speed limit leading up to the curve. So depending on that speed, if they're over it or under it, they'll continue to see a yellow warning or they'll see a red flashing warning. And if they see the red warning, they'll also hear the message curve ahead, reduce speed. But again, if they're already acting safe, they won't hear an audio message. They'll just continue to see the warning. And then lastly, at checkpoint 3, that's right as they're entering the curve. So we turn the screen off so they don't have to spend visual attention looking at the screen. And then we just play a simple short message, reduce speed, if they're exceeding the advisory curve speed. And we don't play any message if they're already under the advisory curve speed. So we have this system kind of blocked out in a general sense. So now what we want to do is look at, are these good design decisions? Will people like it? Will people use it? Things like that. So we come up with these experimental questions to help aid in the design of our pilot study. So the big 3 that we want to look at are system efficacy. Does the system help reduce curve speeds? So for drivers using the system, are their speeds slower than when they don't use the system? The warning criteria. When do drivers want the warnings? So where exactly do you place the different checkpoints? And then user feedback. Do users find the system useful? Do they trust the system? Do they like the system? Would they use it? Questions like that. So to help evaluate these questions, we designed a pilot study. So we implemented this system on a smartphone. Like I mentioned before, we used a Google Pixel. And then we created this system for testing in a controlled field test. So we recruited 24 drivers in the St. Cloud area, which was where our test track was. And we had those drivers interact with our system. And what we did is we varied the warning placements. So we had 4 different treatments, each one corresponding to a slightly different warning placement relative to the curve. And then what we did is we collected the participant data, including their driver behavior, so their speed relative to the position of the curve and in the curve, and also their subjective feedback. So did they like it, usability measures, trust, and then kind of their open-ended feedback about the system. So we conducted the study at the Minnesota Highway Safety and Research Center. Again, this is in St. Cloud. It's right across the highway from the prison, if you know where that is. So this is a driving range that they use primarily for training. They do a lot of ambulance driver training and other emergency responder training. They also do safety programs, things like that. It's associated with St. Cloud State. So we use this track, and we set up a course that went around the perimeter. What we were looking at was we wanted a course with lots of different curves of different radii for the drivers to encounter. And then we also wanted them to be able to get up to highway speeds, so 55 to 60 miles an hour before they encountered the curve. So this shows the advisory curve speeds for each of these curves that we calculated using a ball bank indicator, which is just a device that engineers use to determine what's a safe speed to move through a curve. So based on this, we decided to focus on the two curves at the end of the long straightaway. So the long straightaway at the bottom was long enough for drivers to get up to 55 to 60 miles an hour, and we would have them run in both the directions. We would ask them to get up to speed and then interact with the system as they navigate the curve. So we had them take a few training and test laps without the system running just to get used to our research car. We then collected data during a baseline period where the system wasn't active, but it was collecting data. We had them interact with the system under all 4 treatments, and I'll explain more about those treatments in the next slide. And then we had them interact or navigate the curves without the system under the baseline condition again. So this table summarizes our 4 treatments. And in a very general sense, what we wanted to do was range or have the position of the checkpoint range from too far away to obviously too close, with some points in the middle. And then what we would do is we could use this to kind of see, how sensitive are drivers to the position of these warning checkpoints? Are they very sensitive? Does it really matter? Will they prefer one strongly to another? How close is too close and how far away is too far away? So what we did is we set these distances based on a combination of the deceleration rate required to get from the approach speed to the curve speed. And we also tweaked the distances by hand a little bit to make sure that they felt the same. So additional factors that kind of contributed to that were the road's width. Wider roads feel safer to go faster. Visual traps, what was beyond the curve, kind of these extra factors. So we kind of tweaked the distances closer or further away so that we could get parity between the 35-mile-an-hour curve and the 45-mile-an-hour curve. So in the end, we have these 4 treatments. And for example, treatment 1, there are different distances from the curve depending on which curve you're approaching, but they feel like the same distance away in terms of how early or late the treatments are, or how early or late the warnings are. So this summarizes the driver's behavior results. So this shows the results separately for curve A and curve E that I showed. So these are the curves on either end of the long straightaway. So for curve A, that's when the driver's going through the course counterclockwise. That had an advisory curve speed of 45 miles an hour based on our ball bank testing. When drivers navigated this curve under the baseline condition, so when the warnings were not active but the system was still collecting data, their mean speed through the curve was 43.8 miles an hour. But with the system, it was 38.8. So that's 11% decrease in mean speed when using the system versus or when using the system with warnings versus the baseline condition. Similarly, for curve E, that was not 35, 30 advisory curve speed. We also saw a decrease in mean curve speed between the baseline condition and the treatment condition. So here we're only showing data for treatment 2, which was the most preferred treatment. So other treatments didn't have this same decrease. For example, the warnings that were too late, drivers were still going very fast, but we wanted to look at under the best conditions, under the best treatment, what kind of speed decrease could we expect. So we also looked at subjective measures. So we asked the drivers to fill out forms during the test, forms and questionnaires. So this is one of the ones that we looked at. This is a rating scale of mental effort. So this is where drivers would rate their mental effort required to interact with the system and complete the task. So this ranges from 0 to 150, I think. 0 being absolutely no effort, and 100 being very great effort. So after each run, after each treatment exposure, we would ask the participants to fill this out. So this shows the RSME for the baseline and the 4 treatments. You can see that in general, the lowest mental effort were for the treatments where they were appropriately spaced relative to the curve. For treatment 4, participants experienced higher mental effort completing the task just due to how late the warning was and how frantic that would make them when they needed to brake. One of the other things that we looked at was 9-dimension usability score. So we would ask them to fill this out. And the way that they would read this are, my judgments of the system are, and then they would select, they would put a tick in the box between useful and useless, pleasant and unpleasant, and et cetera. So similarly to the last questionnaire, people did not like the 4th treatment where the warning was too close. In general, people liked treatment 2 a little bit better than the other treatments, but it was very close, especially between 2 and 3, which were both reasonably placed warning distances. We also asked them about system trust. So we had them rate 8 statements from strongly disagree to strongly agree. And then just a sample of some of the statements are: the performance of the system enhanced my driving safety. I trust the system is dependable. I am comfortable with the intent of the system. Statements like that. So we would ask them, based on their experience, how they would rate those statements. So when we aggregate that information, again, you can see that people don't trust the system when the warnings are too close to the curve. And then for other treatments, there's relatively high trust in the system. Between each treatment, we also asked about the timing appropriateness. So we asked if they liked the warnings better, worse, or the same than the treatment from before. And in aggregating that, we find that people feel that treatment 1 and 2, or treatment 1 is too early. 79% of people gave that response. Looking at treatment 2 and 3, people thought those were more appropriate, and everyone thought that treatment 4 was too late. So after the participants did all their driving and we returned to the office, we asked them a handful of questions about the system, what they liked, what they didn't like, and then also solicited kind of open feedback about their experience, if they had any suggestions for improvements, how they would like to use the system if it were an actual product. So overall, people reported that the system was non-distracting. Additionally, we asked them also about use cases where they would like to use the system. A lot of participants responded that it would be good for unfamiliar roads and roads with insufficient signage. We also asked some questions about if they would recommend other people to use the system, and almost everyone said, yes, I think other people should use this system, even if they didn't respond that they should use the system. We asked them about the format of the system. So we implemented it on a smartphone, but we also posed the idea of what if this were available, in Google or Apple Maps? What if it was available as a part of the car's infotainment or center stack? And most people said that they liked it as a standalone smartphone app, although they wouldn't dislike it in those other formats. And then suggestions for improvement. Just because we forced them to experience the system with different timings, a lot of the feedback was based on fixing the timings, tuning those to make them more applicable, or not too early or not too late. Other suggestions for improvement included adding additional features, so like integrating it with a map program or integrating it with Minnesota's 511 app, the driver info app. And 25% of participants did not have any improvements, even after asking them to think about it. So overall, based on these results, we felt that this system is a feasible method for deploying curve speed warnings. The system was well-liked, useful, and trusted among participants, assuming that the warnings were delivered in appropriate distance from the curve. Based on the driver behavior data that we collected, we saw an 8 to 10% decrease in their curve speed when they were using the system. And drivers found the app to be non-distracting when they were using it. Future work that we're looking at different options for extending this would include expanding the pilot testing. So checking different thresholds, really zeroing in on what a good distance is, and other aspects about the system that like the warning designs, the messaging, other system parameters like that. It could include naturalistic field operational testing, so giving the system to the drivers, letting them use the system on real roads, on real routes that they're traveling, so roads they might be familiar with or unfamiliar with, seeing how they like using the system over a longer amount of time. And then other work might be to investigate what the back end would be required for this. So we designed our app specifically to work on this test track, but considerations would need to be made to adapt it in order to use it on a county or a statewide level. So a system for managing the position and the curve speeds for all the curves in a road network, how to deliver that information to the phone, and then how to keep that information updated. So I'd like to acknowledge my research team, who includes Nicole Morris, who is in the back, Jake Achtemeier, who couldn't make it today. This project was funded by Minnesota DOT and the local road research board. And also we had a very good technical advisory panel who included Bradley Astoshin, who was the technical liaison. So I'll take your questions. I think I'm right on time. So, questions? Yes?
We have an online question. It's a two-part question. Since most people would use on unfamiliar roads, it is probably likely they would be running Google Maps or something similar at the same time. And how would those two interact with each other?
So that's a very good question. The question is, how would this system interact with other apps running either in the background or in the foreground? So the app, as we implemented it for this study, was really just to test the warnings. So we designed the app so that we knew nothing else would be running in the background or in the foreground, the app would have complete control over the phone. So the app would potentially need to be modified to run if someone were using other apps, but it would be possible potentially to show pop-up warnings as a driver approaches the curve. It still could play warnings through the speakers, but that's a good point. So care would need to be taken to make sure that it would play nicely with other apps.
She was also wondering, would there be any considerations for road conditions when determining how far in advance the warning should be displayed?
Yeah, so we didn't implement that, but that would definitely be something worth looking into. So if you had information about the current weather for your location, if you knew it was raining, snowy, or icy, things like that, you could definitely modify, how far away the warnings occur, or even how fast the app thinks you should be going through the curves. Yeah.
So I noticed the design of the warning was white, yellow, and red flashing. But when we were showing when there were few on the screen during the set point, I only saw the yellow and the red. So did it have the light?
Yeah, so the idea was originally that we would want these 3 different colors to be 3 different levels of warning. In designing the experiment, we wanted to reduce the number of warnings that the drivers would see, just to help control for the effects of seeing all these different colors. We were really focused on getting feedback about the distance to the curve, so we didn't want to also add in possible confusion about seeing multiple different colors. Yeah.
It's going to be hard to incentivize folks to download and turn this app on all the time, but have you guys researched the feasibility of legislating a mandate for the use of this or other kind of similar safety software?
Yeah, so we haven't looked at that explicitly. There are other safety-related apps that drivers can choose to use. Kind of looking at whether or not it makes sense to legislate that is sort of beyond the scope of what we're focused on. But to your point of drivers selecting to use this, future implementations wouldn't necessarily have to be smartphone-based. So if you had a system that was created or developed by an OEM manufacturer, they would be able to put this into the car, so the driver wouldn't need to actively activate it. They could just have the system available. I think other potential deployment options along those lines would be if this were integrated into a map app, if someone was using like Google Maps, say, and the system could also give them information about that, then there might be a little bit less of a barrier to, oh, I'm getting in my car, and now I have to also put my phone somewhere where I can see and hear it, and also activate this app to run in the background. But yeah, that's a good point.
What was the demographics of the pool of subjects that were used in the test?
We had 24 participants between the ages of 20 and 40. We wanted to look at a population of drivers who we were assuming would be relatively familiar with a smartphone, and also just to avoid any differences between drivers of different age groups. So we wanted to cast kind of a narrow net, at least at first, to make sure that difference in curve behavior might be different between younger and older drivers, for example. So we wanted to make sure that we weren't also adding in those factors too.
Were these people from rural areas or from urban areas?
We recruited in the St. Cloud area, so almost everyone was from that area, living in an area, or living in St. Cloud or one of the surrounding cities or towns. So overall, the drivers did less urban driving than rural driving, based on their self-reported kind of driving histories. Yeah.
It seems to me that driven a couple of late model cars, 2 years old or less, that have speed indicators, speed limit indicators in the map app, in the map program. In other words, the speed is up on the screen, and it does flash red when you're exceeding the number. And I'm wondering, do you have an idea of whether or not the actual speed limits for corners could be integrated into that? Because it doesn't deal with the speed limits in corners. It deals with the main speed limit. These are satellite-based. Almost all the nav systems in cars now are satellite-based. They're not based on cell phones. So their GPS capability is a little tighter. But, I mean, have you investigated that?
Yeah, so that's definitely one possible way to deploy these warnings would be integrating it into a car. So especially if a car was already giving you warnings about your speed on straight segments, potentially that could be extended to give warnings based on information about curves.
Has the Intelligent Vehicles Laboratory surveyed the population of new cars and what their speed limit capabilities are on their map systems?
We have not.
Okay. That might be a recommendation.
Okay, I think that's all the questions.
Well, if there are no further questions, none on the internet, let's join me in thanking our speaker. And just want to remind you that there is no seminar a week from today. That's April 5th. There's no seminar scheduled then, but 2 weeks from today, on April 12th, we will have Professor Raj Rajamani speaking on smart human-centered collision prevention systems for bicycles. So that's 2 weeks from today, not next week, so don't tune in next week, and we'll see you all on April 12th. Thank you very much.
No, as an example, the navigation system on GM cars, that comes from us. Right. The satellite, the navigation system on our Subaru comes by satellite. That's a satellite communication. It's not cell phone.
No, I get it's not cell phone, but if it's satellite, it must be coming through XM or something.
I think that's how they communicate. The mechanism they use. Yeah. I think it was the Subaru that has the speed limit indicator in it.
It does?
Yeah. Now, I
How
have.
many people have that feature?
That's what I want to know. That's what I want. I have a radar detector that has a map system. It's the Escort.
Right.
The old Escort system. That had a map system with a very distinct speed limit indicator that was very accurate. I mean, that sucker would change within 100 feet of the sign.
But was it correct? Rural area?
Yeah, I mean, way out in the middle of nowhere. That was satellite based. That was not cell phone based. And I mean, in northern Montana,
I think it's,
it worked.
I think in terms of it.
And it was very effective.
That was through this Escort radar.
The Escort radar detector.
But I wonder